The other thing we need to talk about is, on interrupts, what do I save on the stack? In general, you get an interrupt, what do you have to save on the stack? Program counter? Yeah, well that's saved. Hardware does that. What else? Registers. Which registers?
All the registers.
All what registers? All the caller. I'll call it now. Well, let me simplify it maybe. Save the registers that might be altered by you, right? Okay. Do I have to save all of them? That's hundreds. Oh man, they take a long time, a lot of memory. No. Well, if I'm writing an assembler and I use 3 instructions or 3 registers, I just need to save 3 registers. That's the nice thing about writing assembler. But nobody's done that since the 1900s. So we're all going to write in C. Okay? So whatever registers C might use without restoring, I better save those on the stack. And there's a convention that all the power architecture devices follow. There's an application binary interface. It's actually embedded application binary interface, now called E500 EABI, that was done in the 1990s, and it was based on an existing one for Unix. And so it basically says, okay, compilers, when you call function foo, certain registers can be volatile, scratch registers. You can alter them, and when you return, they can have different values, and that's okay. And compilers will know this and will behave that way. And if we do change anything other than these volatile or scratch registers, we'll put them on the stack first and then restore them before you return. Okay. So if you're a interrupt, though, you know, since every register has to be put back to its original value, if you call a C function, that C function is going to change all those volatile registers, or it could. So I have to put on the stack those volatile registers that a C function would call. And what you see here in this stack frame here is these are the registers that are volatile to a C function. And so they have to put on the stack. And so it's very straightforward. We give you the code to do that. And if you use a Code Warrior Pragma interrupt, it'll do the same thing. Same thing for the other compilers as well. So the prologue then is going to, this is the assembly code, pseudo assembly code. And I'm going to create a stack frame. And the way stacks works is we don't have a stack pointer. There's no special register that's a stack pointer. So, but we have 32 general purpose registers, 0 to 31, R0 to R31. And so we have this software convention, this EABI. We picked one. Everyone uses R1. Everyone in the world, all the Unix guys, we all do it. And so R1 we'll use as a stack pointer, but we only decrement it once. And then we increment it to, we store offsets on top of that. So we create a stack frame by decrementing the stack pointer 80 bytes, and then we can put stuff on it as positive offsets. So we decrement the stack pointer, we save the value, then we save the machine state. Also, we read who did the interrupt. Now we can read enable interrupts. So right here, we can read enable interrupts, and now we save all the other registers, and we eventually will branch to our ISR and return. What I'd like to do now is hook up the board, but let me show you a shortcut. Can I borrow your board here? I think my board's still back there. Let me just plug in. For our next trick, I want you to go to the projects. You know, they're in the Code Warrior examples. And let's start with software vector mode. Go in that directory, and once again, we're going to start the project, the Code Warrior project. And I still have the old one here. I can get rid of it. Just get rid of the windows I don't need. It's all here, all the sources here. I'm just going to compile it. And then I'm going to, if you notice here, I've got two projects actually. I can program it to flash, or I can just download to RAM. And that's controlled by these RAM settings. So watch here, just to learn a little bit of basics of the debugger. This is where, to control a project, these are my settings. So I click on it, and for this RAM project, here's the name, which matches up here in the window. Here's the target. This is my output file name. This is the build extras. This is where I invoke a debugger, which is specified here, pass these arguments, and give it an initial directory. And there are other settings. So, and it'd be similar if I go to a flash, click on the settings for that. Here it's named flash, etc. So I'm going to go ahead and build the RAM. I've done that, and now I can just click on the debug and bring up the debugger. Now I'm going to show you another neat trick. You know, rather than typing all this stuff, and you see I've got variables here that, let me get rid of these here. I'm just going to hit delete, click and delete. Rather than retype stuff all the time, I can have a debugger batch file for macros, as they're called. So this is the macro button right up here, play macro. I play it, and it asks for a file. Well, actually I have to go up one directory, and then there's debugger macros right here. And in here I've got one. If I've compiled it and programmed it to flash, I can just come back here and do this, and let's just take a look at that. Let me just open it. It's just a text file, very simple. Here's the name of the file, and here is the command high-level load to load that ELF file. Go till main, so I don't have to type that. Clear the variable windows, and then put a variable in the window called pit counter and software IRQ4 counter, so I can display these. So I can run that. Just click on that and play that macro, and it loads it for me. It's downloading. Okay, my hands are off the keyboard. It runs to main, and look over here. I've got these. Unfortunately though, these are in hex. I want decimal. So I have to manually convert these, modify it to be decimal. So I'm going to click on it, and then right mouse click, modify variable. And here I click modify, and then decimal, and OK. Let me do that again for the other one. Right click, modify variable, check modify display properties, check decimal, OK. So now I can run, and what this does, it counts milliseconds. So I'm going to just hit run here. Before we were stepping like this manually. Well, there's this middle button here, just does it continuously but kind of in slow motion. And then, but I can just hit go, and so now I'm going, let's see, it's about 1 second, 2 seconds, 3 seconds, halt. And well, I think it was running for 5 seconds, because this counted 5,200 milliseconds. And this is, so that was for my 1 millisecond task, and I had half of that for a 2 millisecond task. So I can count again. I'm at 5, so 6,000, 7,000, 8,000. Yeah, not far off. And I can, if I want to have a breakpoint, I check on a red dot, double click. Now I hit a breakpoint, and every time I run, breakpoint. If I want to go to a certain instruction, there's little blue arrows. I can double click on it, and I'll go to there. Then I can hit run. Clear the breakpoint, and just clear. Now, what do I have to do if I want a peripheral, a different peripheral to give me an interrupt? For software vector mode, I initialize a peripheral, which you'll see here, like init pit. So you can use this. Okay, I do my stuff, I enable interrupts, and I hit the interrupt PSR, the priority. So I give it a priority, I configure the peripheral. Okay, and if I want to do it for a CAN, I do the same thing and do whatever specific initialization I want, enable interrupts for the CAN, give it a priority, but then I have to give it the vector for the interrupt service routine. And this is the table for software vector interrupts, the interrupt service routine. And so you can see most of these are just dummies. We have a pretty big family. Well, that's good news. We have a pretty big family of power architecture devices. But powertrain uses different peripherals than body controllers and then instrument clusters. So they have different interrupts that don't exist on and aren't needed for the other devices. So something like a PIT interrupt might be number X on a powertrain device, but number Y on a body controller. So I put comments in here because I use this for all, just to show the differences for all the power architecture family for automotive. But you have to find your interrupt number and then put it here, substitute it here. And the question is, how do I find my interrupt number? And that's in the reference manual, which I happen to have handy. You go to the interrupt chapter, and I just, something like this, a big table, I just scroll down until I see a big table. Oh, here it is. So here's my table. And these are my core interrupts, but these are the interrupts, software flags, but you can see here, DMA here, interrupt 10, etc. Here's, let's find something interesting. Here are the pits, 59, 60, 61 in this case. A to D, 62, 63, etc. So there's a big table of all the interrupt numbers. So you find your interrupt number, then you can go back to the code and plug it in for the right ISR, your address. Okay, so why don't you take time, download, play with the interrupt controller, put some breakpoints in there, execute it, have it run. I want to see if there's any questions. This is probably the next most important one. I've got one other example we might do for the A to D, time permitting, but I think we're on schedule. It's a lot of material, and I don't expect you to remember it. It's just to give you a flavor of what's in the slides, what's in the examples, and pick up a few things of what's different. I mean, that's our intent for this training.